Welcome to this explainer. Today, we are stepping right into our virtual lab for a really fascinating journey. We're going from the invisible, totally unseen energy of chemical reactions all the way to synthesizing and purifying actual physical compounds. And hey, my promise to you is to keep it simple. We're going to strip away all the confusion and explain everything super clearly, using crisp text and detailed pictures to guide you every step of the way. So let's jump right in.
Okay, here's our quick agenda for this experiment. First up, we'll look at the energy of reactions. Then, preparing chemical salts. Third, we'll break down mixtures and solutions. And finally, purifying the final product.
All right, section 1, the energy of reactions and thermal energy transfer. Let's go.
So here's the deal. Chemical reactions happen because elements want to reach a more stable energy state, right? They do this by breaking old bonds and making new ones, and this whole process either releases or absorbs energy. Now, if thermal energy gets released out into the surroundings, like into a test tube or the air around it, making things hotter, we call that exothermic. Think of lighting a match or snapping one of those winter hand warmers. But if a reaction actively takes in thermal energy, actually cooling down its surroundings, that's endothermic. It's exactly how an instant cold pack for a sports injury works.
And this setup brilliantly shows what's happening to our surroundings. Notice how the exothermic reaction on the right is actively pushing heat out into the test tube and the air. Meanwhile, the endothermic reaction on the left is literally pulling heat inward. That's exactly why if you were holding that left test tube, it would feel super cold to the touch. Now you might be wondering, how do we actually map this out? Well, take a look at these charts. In an exothermic pathway, the reactants start off with a whole lot of energy. And as the reaction happens, that energy plummets downward, releasing into the world. Simple, right? But endothermic pathways, they require an upward climb. The reactants actually have lower energy than the final products, which means energy absolutely has to be absorbed from the outside to make the whole shebang happen.
Moving right along to section 2, preparing chemical salts and synthesizing compounds. Before we start just throwing chemicals together, we absolutely have to check our rules. This table is our starting point. As you'll see, it clearly lays out that while all nitrates, sodium and potassium salts easily dissolve in water, we'd have a much harder time trying to dissolve something like silver chloride or most carbonates. And this is absolutely crucial, because knowing whether our target salt is soluble or insoluble dictates exactly which experimental method we have to use.
For instance, if our starting metal or base is safe and insoluble, we go with method A, excess neutralization. Basically, we add an excess amount of a solid, like say zinc or iron oxide, to an acid until literally no more will dissolve. This guarantees that every single drop of the acid reacts. Then we just filter out that leftover unreacted solid, which leaves us with a nice liquid salt solution. Finally, we gently heat that liquid to evaporate the solvent until we hit the crystallization point. We let it cool, and boom, we harvest our brand new salt crystals.
But wait, what if both our acid and our alkali are soluble? Well, we can't exactly filter out the excess then, can we? So we pivot to method B, which is titration. We use a highly precise long glass tube called a burette to carefully drop acid into a known volume of alkali in a flask below. We add an indicator like methyl orange, which changes color the exact millisecond the solution is perfectly neutralized. Oh, and a quick pro tip here, always rinse your burette with your acid first, not just water, so you don't accidentally dilute your concentration. Trust me on that one.
Okay, on to section 3, understanding mixtures and solutions and the mechanics of mixing.
Let's get our vocab straight real quick for this one. The solid substance we are trying to dissolve, like the salt we just synthesized or even just regular table sugar, is called the solute. The liquid doing all the heavy lifting, which 9 times out of 10 is water, is the solvent. And when they come together, perfectly mixed so the solid seems to just disappear, that creates a solution.
Let's actually watch how this builds. Look at the left side. You can see the individual sugar solute particles breaking apart and just vanishing right into the empty spaces between the water solvent particles. Pretty cool. But on the right, we hit a wall. If we keep dumping in sugar until no more can possibly dissolve at that temperature, the extra sugar just piles up at the bottom. When that happens, we've created what chemists call a saturated solution. Which brings us to section 4, purifying the final product and isolating compounds.
Because, let's face it, real-life chemistry is rarely perfectly clean right out of the gate. The most basic way to separate an undissolved, insoluble solid from a liquid is simple filtration. We pour the mixture into a filter funnel lined with paper. The liquid molecules are tiny enough to flow right through the microscopic pores in the paper. We call this liquid the filtrate. But those larger solid particles, they get trapped up top, becoming what we call the residue.
Now, what if we want to extract a liquid solvent from a dissolved solid? Like, say we want pure drinkable water out of an aqueous copper sulfate solution. For that, we use simple distillation. We heat the flask until the volatile water boils completely into steam. Since the solid copper sulfate has a massively higher boiling point, it just stays behind in the flask. The steam then travels down a cooling tube, a condenser, where it turns back into perfectly pure liquid water.
Okay, but what if things get trickier and we need to separate two liquids that are completely mixed together, like ethanol and water? They both boil, right? Just at different temperatures. This is where we use fractional distillation. We use a tall column packed with tiny glass beads attached to our boiling flask. As both liquids start to evaporate and rise, the beads catch and cool the liquid with the higher boiling point, forcing it back down. This allows only the more volatile liquid, the one with the lower boiling point, to successfully make it all the way over into the condenser. It's an absolutely brilliant technique, and it's literally how the industry refines crude oil. Finally, if we want to check the absolute purity of a dissolved substance, or maybe separate out the different food colorings in a piece of candy, we use paper chromatography. We draw a baseline in pencil, because pencil won't dissolve, place little spots of our chemicals, and dip the very bottom of the paper into a solvent. As that solvent travels up the paper, it carries the compounds along for the ride. Because every single compound has a slightly different solubility, they travel upward at slightly different speeds. It's like a race, separating them perfectly into distinct little dots. But we're not just eyeballing it. We quantify that purity using a super precise math formula for the retention factor, or RF value. We take the distance the center of the spot traveled from our baseline and divide it by the total distance the solvent front traveled. Because most pure substances have a highly specific, known RF value, doing this quick math lets us uniquely identify our chemical. It's basically like dusting for chemical fingerprints.
And there you have it, from understanding the thermal energy of reacting bonds to making salts, and finally isolating pure chemicals using some incredibly clear visual tools. We've seen exactly how chemists can manipulate matter with absolute precision. So I want to leave you with a thought. If you could take these powerful separation techniques and apply them to the complex mixtures you interact with every single day, like your morning coffee, the air in your living room, or even the ink in your pen, what hidden, pure substances do you think you'd discover? Thanks so much for joining me in the lab today on this explainer, and definitely keep exploring the elements around you.